Let me just tell you, though, that we can take this incorrect isomer, epimerize it, and in the same reaction, reduce it with lithium aluminum hydride to get to this intermediate. We can oxidatively convert the allyl side chain into a carboxylic acid, allylate the secondary alcohol, and convert the carboxylic acid into a new diazoketone, and repeat the process, all in more or less good yield, except for this one right here. Forming the diazoketone is not such a good reaction. And as before, we get the axial allyl group, but we can epimerize that using DBU. And we were pretty excited about using, this is a 5-step sequence to go from here to here. We were pretty excited about using that in the context of the marine polyether ladder toxins, such as this one here, Yesotoxin. And I think it would be applicable to the polypyran domains. But what concerned us was this chemistry was absolutely unsuccessful for making larger ether rings. So in order to build a molecule like Yesotoxin, we would need to have other chemistry to make these hinge large ring ether regions. And the oxonium chemistry didn't look like it was going to solve that problem. Now, towards the end of the seminar, I'll come back to this question and show you a way that we can make medium-sized ethers using ylide rearrangement chemistry, but not the same sort. So instead, let me move on to another type of cyclic ylide, an ammonium ylide. And this ammonium ylide is very easy to generate, starting with a secondary amine and this bromodiazoketone. And in the presence of triethylamine, we can generate the amino diazoketone, directly convert that into these piperidones using rhodium acetate. And as long as R1 here is a good stabilizing group, we get these products in great yield. The only downside was this only worked to make the 6-membered ring. So larger rings didn't work or barely worked. Smaller rings also didn't work, which surprised us a little bit and caused us concern about being able to use this as a general way of making alkaloid targets. But it was around this time that we first discovered that soluble copper-2 catalysts were much more effective in many cases for affecting these ylide-involved reactions. And so, for example, this series of substrates where N varies from 0 to 3 works in all cases using copper-2 ACAC 10 mole percent to give us the pyrrolidinone, the 7 or even the 8-membered ring, and what I would consider to be a pretty acceptable yield considering the difficulty in reaching around and forming that reactive 8-membered ring. So, so for the most part, we've concentrated on copper-based catalysts for this chemistry. Here's one example where we didn't. And the reason why we're not talking about transition metal activation here is we wanted to study the question of what happens when we have a stereogenic center at nitrogen. Because of course, as a quaternary nitrogen, a quaternary ammonium, this is a stereogenic center. It has 4 different groups attached to this tetrahedral nitrogen. And in this particular case, it's encased within a ring. So when that group, one of these groups on the nitrogen migrates, it's going to migrate either from the bottom or from the top of this ring. And the question we wanted to ask is, will there be a memory effect? Will this migration occur with transfer of chirality? And it was difficult to explore that question using the transition metal catalyst because we couldn't really tell what kind of ammonium ylide we were forming. So here we did it in a very controlled way. We generated these ammonium salts from amino acid derivatives with very, very high degree of diastereoselectivity. So in each case, we have one or more other stereocenters here that are controlling the configuration at the nitrogen atom. Once we've crystallized these to a single diastereomer, we treat them with base. That destroys this adjacent stereocenter to make these planar ylides, but we still have stereochemistry at nitrogen. And so the question is, does that stereochemistry at nitrogen control the eventual stereochemistry at carbon? And the answer is yes, it does, most particularly in the 2-3 shifts. In the 2-3 shifts, the chirality transfer is complete, as we would expect from a concerted reaction, because in each of these reactions, the second and the fourth, we're going to start bonding to this carbon while we're breaking this carbon. So if this bond is pointing up, this bond has to point up as well. On the other hand, as you might expect from a stepwise dissociative mechanism, with the benzyl migration, we see partial but not complete chirality transfer, something like 2-to-1 or 3-to-1 in favor of the product of retention, but significant amounts of randomization, which you might expect. If you really had a radical pair intermediate, some of that radical pair could diffuse out of the solvent cage, and then it would no longer, the benzyl radical would no longer remember whether it started out below the ring or above the ring. And of course, these conditions here are not optimum for a highly structured solvent cage. So we did see some diffusion out of the solvent cage, and instead of the high stereoselectivity we saw here, it was moderate. Nevertheless, we thought this 1-2 shift could be used for a stereoselective process with chirality transfer in a slightly modified situation. So now here, what I'm talking about is we have a nitrogen, it's 6 atoms away from a diazoketone, and next to that nitrogen atom is this chiral center. So this is derived from proline. And when we treat this with copper acac in good yield, we get these two quinolizidine products, with this one predominating 19-to-1. And the major product can, in 3 additional steps, be converted to the alkaloid epileupanine. So overall, 5 steps from proline ester to epileupanine with good diastereo control. What about enantioselectivity, though? 75% EE. All right, so we got to remember that number. But let's try to explain the 95-to-5 first. Our sort of starting explanation would be this. There's 2 possible ammonium ylids that can be formed when this metallocarbene and this nitrogen react. The metallocarbene can either approach from the bottom, away from the ester, or from the top, on the same side as the ester. From the bottom would give us this ylid, from the top would give us this ylid. And now if each of these ylids rearranged with complete retention, we would get each of these diastereomeric quinolizidines. And if this is the major one, then that would mean this was the major ylid. But if this were the only mechanism, then each of these products would be formed with 100% enantiomeric excess. And clearly that's not what we're seeing. We're seeing some significant amount of racemization during this reaction. So there has to be a second racemic mechanism. And that, I think, would come from the idea that when we break this carbon-nitrogen bond to generate a radical pair, if that biradical has any lifetime, it can relax, it can randomize by bond rotation to give us a biradical that no longer remembers what ylid it came from or what the original configuration at this ester substituted carbon was. Because look, this is completely achiral. Now this can recombine, and I think it should recombine preferentially to give this diastereomer based on simple sort of Newman projection steric arguments. And so this random mechanism to give a racemic product should favor this diastereomer. But look, 75% EE means most of it actually did go through that first pathway where we form this ylid and migrate with retention. And so we also have to explain why would we make this ylid in preference to this ylid? And why would it migrate with retention when it would seem that we should lose all our stereochemical information when it does the homolytic cleavage? Well,